Everyone, so we've talked a lot about how light travels, how quickly it travels, the straight paths that it takes, the particle-like nature of it reflecting off of things and having those photons hit our eyes, which tells us what?
It tells us that everything we see in the universe has happened in the past.
So when I look at you, it's as you were a few nanoseconds ago.
Yes.
Knowing that light acts as a particle and does the things that we do, we then come to another experiment that people have done with light. It's called the double slit experiment. And what you'd think is that if light is particles, like little sand particles here, they'd hit those two slits, they'd go straight to the screen, and they'd start filling up two little lines.
Yeah, I would think two little lines.
But this is what actually happens.
Well, that's crazy.
So
how does that actually happen? I'm seeing dots and waveforms and strange things.
This really messed with people because if light was acting as particles, why would you get all these dots to form up? If light is energy, energy can travel in many different ways. So if we take a look at this candy wave machine that we constructed, if I wanted to put energy into this machine, I would have to just shake it. And once energy is put into the machine, what are you seeing?
I'm seeing a wave travel all the way through this thing.
When you say wave, what's actually moving up and down, and what's moving along the tape?
Well, the candy itself and the things connecting it are moving up and down, while energy that's causing that to happen is moving along the tape.
So energy propagates down the tape, while the individual little pieces of candy shake back and forth, and the medium moves in a different direction than the actual energy.
Right. And it reflects back. You can see it go down to the wall, bounce back, and the energy comes right back through the tape again.
So if we agree that light is a form of energy, then light can also travel as a wave. And in this case, it travels in oscillating electric and magnetic fields, which is why we call it electromagnetic radiation. It's a self-propagating wave that travels through space, and this electric magnetic wave carries the energy and carries the photons along with it. Light travels as a wave. There's some observations we can make about waves. What are you observing?
There's a pole attached to a string, basically. And as that pole oscillates up and down, it sends energy through the string, making a wave.
Is there anything we can measure from this wave?
Sure, I could look at it. I can see like it makes different parts of a wave. Like I can see the tops of the wave. I can see what appear to be the bottoms of the wave, and all points in between. So I could measure that distance.
Okay, and if I measure that distance, so if I take a ruler here and go from the top of a wave to the other top of the wave, we would call that the
wavelength.
The wavelength. From top to top would be crest to crest. Where else could be the same wavelength?
Yeah, how about bottom to bottom, or trough to trough?
Trough to trough works. What if I picked the midpoint right here? If that is the start of my wave, where is the end of my wave?
Where that happens again.
Where that happens again, so right here.
And that's going up.
That's going up. Oh, so I'm going
You're
down
going
here.
down.
So when I go down again.
Yes.
So that is one full wavelength. As long as it's identical points on your wave, or you can measure a wavelength. I could look at that window and I could actually count how many peaks go through every single second. That would tell me what?
Well, that would give you frequency.
Frequency, which would be how many things happen per second. Yeah. So I could time the wave and get how many waves go past per second, which would help me find the speed of the wave. Now we can also change some stuff, like I could decrease the frequency of the wave. And what are we seeing?
I'm seeing a much longer wave.
So it's a bit much wider. We get bigger distances between crests and crests and troughs and troughs. And if we increase that frequency,
we're getting much smaller distances between the crests and the troughs, which means I think that would hurt more if it hit me.
Why? Why would it hurt more if it hit you?
It seems like there's more energy going through it.
So more frequency seems to go with more energy, and it also corresponds to lower wavelength. So with us knowing the speed of a light wave, and knowing the speed of light is constant, changing the frequency of a light wave does what to it?
Changes the amount of energy that's being produced by that portion of light.
Okay, so if I increase frequency, I would see
a shorter wavelength.
And vice versa.
And vice versa.
Lower frequency,
longer
waves. So I'm going back to the candy wave again here. If I shake the machine at a particular rate, I can see that I'm getting a particular frequency and wavelength. This looks like a very long distance between the two very excited sides of the candy wave.
Oh, wow. Well, now you're shaking a little bit faster, and you can see that the crests are traveling through at a much greater rate, so that's an increase in frequency, and the wavelengths are shorter. I see they're closer together.
So that means that when white light hits a medium, whether it's glass or water or anything like that, since white light is composed of all the colors of the rainbow, that's why when we saw that pattern happening in the double slit, we saw that different colors of light expanded as well.
Sure. As the white light hits the prism in this particular case, all the different wavelengths bend slightly differently, and therefore you get separation of color.
Most of the light that's in the universe is actually invisible to us. When we look out there, we're only seeing a very small portion of light that is actually sensitive to our eyes. That's between 400 and 700 nanometers for the visible light we're seeing here from red to purple. So a higher energy, higher frequency, shorter wavelength light that can be damaging to us is what?
Ultraviolet.
And why do we worry about ultraviolet?
Well, we worry about ultraviolet because when it strikes our skin, it can cause burning and damage over long term.
Because it's shorter wavelengths, higher frequency,
and a lot more energy.
Still traveling light speed, but just a shorter wave. And an even more energetic and more damaging form of light can pass right through your body.
Yeah, X-rays are something that you should try to avoid if you can. If you are going to get a lot of X-rays, insist on the big vest because it protects you from those energetic waves.
And the technicians always run away.
They do. They run and hide.
And even higher energetic light, shortest wavelengths that we see are gamma rays. These can destroy living tissue.
Right, gamma rays, their wavelengths are so small that they can actually pass through metals. You need a very thick layer of lead to be able to stop it. If it's a thin layer of lead, it'll still pass through.
These are some of the things you have to worry about in terms of light coming from the sun if you're traveling to different planets or different stars. Our atmosphere is actually really good at blocking gamma rays, X-rays, and most of the ultraviolet.
Most of them, yeah.
So something that would be slower on the other end of the electromagnetic spectrum would be something that shakes with a larger wavelength, lower frequency, and it's really the light that hot objects emit.
Right, they call that infrared light.
Because that's beyond red.
That's right.
So it's invisible to us, still traveling light speed, but we can't see it because of the wavelengths.
It's not inherently dangerous like everything else at this end of the spectrum because of the low energy levels. Case in point, infrared remote control.
And then even longer wavelengths are things that we use to cook with or send our text messages. Those are
microwaves.
And then even lower energy and the longest wavelengths in the electromagnetic spectrum are how radio stations send us their information. They don't send sound from the station to your car, they send light.
And there is information that's piggybacked on those radio waves that then your tuner interprets.
And converts it back to sound for you. So when you drive past a radio station, you won't hear them. So we've got the basic 7 forms of light here, increasing frequencies and energies, and decreasing wavelengths as you go from the radio wave at the longest waves all the way through the visible spectrum. You can see it's that tiny little strip we talked about, from red being the longest wavelengths and blue being the shorter wavelengths. And if you wanted to say that ultraviolet is even shorter than visible light, you could say ultraviolet is bluer than visible light.
You could. So rather than saying the right or the left side of the electromagnetic spectrum, which this is, we like to say the blue end or the red end of the electromagnetic spectrum.
There are many forms of light. It all depends on the wavelength and frequency of what type of light you're looking at. We can't see most of the light that comes to us from the universe. We have to build special telescopes to detect each of these different wavelengths. But when we do look at the cosmos that way, we get a brand new perspective and a whole new view of what the world actually looks like. So we'll talk more about that next time. Stay tuned for some infrared fun. So what we're doing here in the first example is we have 2 cameras. One is your normal camera that picks up all the visible light you can see, and the other is an infrared camera that's actually picking up the heat signatures from these objects.
Right, and when we look at heat, you can kind of think of how a snake might view the world. They see body heat, or the lack thereof. In this particular case, you can see the cold water pouring into a vat, and it's the darker colors that are the colder colors that we view, and the lighter images are warmer.
So you can see when I put my hand in the water, it looks like I've got some substance all over my hand, and really my hand has just cooled off. So now we switched up temperatures. We've put on the hot water in the sink, and it looks like I'm pouring lava into the sink.
Again, it's just a combination of the hot and the cold colors. The hot colors look like the lava. Now we're going to pour some of that lava into the cold water.
And you can see in the visible spectrum, it's just me pouring hot water into cold water. It doesn't look any different in real life, but if you had infrared vision, you can see me pour that hot water in, you can see the change in color.
Yes, you can.
And you can actually see the water warm up. So in this last video here, what we got is, again, the visible spectrum on the one camera, and we've got the infrared on the second camera. And you can see that you are hot.
I really am.
Your hands are super hot, your face is super hot. You can see the clothes are not the same temperature.
No, they're not. They act as a pretty good insulator.
And now you can see the floor is a certain temperature, but what are you doing?
I'm applying a lot of friction.
And when you do that, you actually leave a streak behind. You can see in the visible spectrum, we don't see anything on the floor, but in the infrared section, you're actually leaving a long streak behind.
Mm-hmm. Well, my warm hands on a cold table will probably leave a warmer table, but let's see what happens. Yes, they do.
So you can see zoomed in the visible spectrum, I see nothing, but in the infrared, I can see your handprints left behind.
Not quite as hot as the originals, but pretty close.
And so the last demonstration we got here, you're going to put your hand in just colder water, and when we look at your hand, when you pull it back out,
it's a darker color, which means that it has lowered its temperature.
So your one hand is around 30-some degrees Celsius, and the hand that's back in the water, one more time,
even colder.
Ooh, sitting down there around 25 degrees Celsius. So your hand has cooled down, but you can see visibly it looks just the same. That's the fun we can have with infrared cameras. We may do some in class. We'll see you next time.
Say that.